So thank you so much to all of you. Thank you to the organizers for the opportunity, and thanks to all of you for taking time out of your busy schedules, either to be here in person or to be online. Really excited for the next 2 days, and it's really a privilege to be able to kick us off, well, after this really nice introduction to what is artificial intelligence. I'm going to give you another definition of AI. So we had artificial intelligence, data intelligence, and in a couple slides, I'll give you sort of my other overarching definition. So first, I just wanted to start off with something I think is a little bit fun. So I took my abstract that I wrote for this talk on, AI's role in modern toxicology from data to decisions, and I put it into ChatGPT 4.0, and I said, please create a figure that captures all of the key concepts in this abstract. And so this is what it came up with. It's pretty attractive, like it's very visually appealing, and it's got, I think, many of the aspects that we would like to see in terms of data and databases. But when you start to look a little bit closer, you see that there's a lot of nonsensical aspects of this as well. So it's got things like databases, which, well, actually that kind of makes a little bit of sense. We do have databases of data and databases of databases of data. That's fine. But chemical safety ons, that's a new one for me. I don't know what that means. But something biological safety inputs, chemical death viruses, that's also a new one for me. So this is just kind of showing you how, while AI is powerful currently, you can't just let it loose on its own, right? There's a lot that it still doesn't understand. One of the reasons that large language models have trouble with images is because they are actually trained on images and they don't recognize text as text when it appears as images. The tokens are really of visual aspects as opposed to seeing letters and words within images. And so there's a lot more training that has to be done before something like a really relevant and informative figure could be generated by AI on its own. And I really just put that up to demonstrate the necessity of having the human in the loop. I think that AI is probably the most powerful tool that is transforming science and, has massive potential for chemical safety assessments. But I don't think that we will ever really get to the stage where we can just let it do its thing on its own. We have to have the human in the loop, which is why I really like this definition of AI as augmented intelligence. So rather than just this autonomous technological system that's going to replace us, it's using everything in our technological repertoire to enhance and complement human intelligence in a way that really allows us to build out our toolbox to be much more effective. And this is not a new concept. This is a concept that was really published in the late 50s and early 60s, and I think is really now coming to bear fruit in the era of deep neural networks and large language models that we've seen explode over the last couple of years. So as David and Blanca introduced me, I am working as the director of ICCVAM, which is the U.S. Federal Resource for Validation of Alternatives. I also direct the National Center that provides support to ICCVAM and the 18 different federal agencies that belong to ICCVAM. I also work as the co-coordinator of the U.S. National co-coordinator for the OECD Test Guidelines Program. And most recently, I've been leading the development of a new NIH grant program that I want to talk to you about for just a couple slides in the beginning, because it's quite relevant, I think, in terms of the future of connecting biomedical research to application in chemical safety assessment. Historically, I think there's been a dichotomy between basic research, human mechanistic disease understanding, and toxicology. And I think that's really a false distinction. I think they exist along the same continuum, and it's really, really important to have one feeding into the other via novel approaches to validation and qualification. So I'm going to talk to you about sort of each aspect of this continuum and where AI fits in those. First, just to make you aware, there is a new NIH grant program that will be somewhere in the neighborhood of $300 to $400 million invested over the next 10 years to catalyze the development, standardization, validation, and use of human-based NAMs. Specifically with application to human disease understanding across diverse populations and basic biomedical research. but also with an eye towards validating those technologies and supporting their implementation into regulatory policy and use. And AI is really fundamental to the combinatorial NAMs that we envision being funded under complementary. And while it is a requirement from the NIH that the principal investigator on any NIH-funded grant is based in the US, they can have as many international collaborators as they see fit. So I would encourage you to reach out to your American colleagues if you have good ideas. And basically, what we'd like to see here is we have all of these kind of disparate and individual projects that have been ongoing over the last several decades in silico systems models, digital twins, artificial intelligence, machine learning, complex in vitro systems, high throughput screening. But what we'd really like to see for these grants and really to push the envelope and develop much more comprehensive strategies that provide insights into human health and disease pathways and their susceptibility to exogenous perturbations is combinatorial approaches. And we really see AI as fundamental to bringing these different data streams together and both interpreting those high volume, high content, complex data sources, but also generating testable hypotheses that can feed forward into that loop of NAMs data generation and application in chemical assessment. We did a lot of strategic planning efforts over the last year and a half to pull together the detailed implementation plan of complementary. And one of the areas where I think AI has been really, really transformative and where we leveraged it extremely effectively is to do a landscape analysis of the existing biomedical research literature and how NAMs are being used currently in biomedical research. And so we were tasked, and I say we because it was actually my group, NICEATM, who did this part of the strategic planning effort for complementary. We were tasked with doing a comprehensive review of NAMs in biomedical research across the scientific literature, something that would normally take at least 18 months from start to finish, and we had 3 months to do it. And I said, okay, well, this will be impossible unless we use generative AI. And so we essentially developed a whole new protocol for systematic literature review that relies very, very heavily on generative AI and subject matter experts in the loop to do very specific prompt engineering to both identify papers in the literature for NAMs use in biomedical research and extract information from those papers, and then do a real assessment of where we have good coverage and where we have opportunities and gaps. And some of the real opportunities that we identified were not a huge surprise to us. This was really confirmatory towards some of the focal areas that we had already identified for complementary. Things like incorporating variability in population-based responses, diversity, susceptibility, sensitive subpopulations, looking much more towards application in regulatory use and validation and qualification of methods, and both ethical and economic considerations in NAMs for biomedical research. We also, as a sort of side project to this landscape analysis, we did a fairly comprehensive kind of survey of all of the different data resources that are out there. So things like HubMap or gene ontology, and we applied a fair assessment rubric. So fair, findable, accessible, interoperable, reusable, to see how many of these existing data resources were 100% fair and how we could use them as a starting point for building the complementary data hub. So this is a comprehensive center model. All of these different pieces will be funded via various grant opportunities. But the one that, of course, I'm the most engaged in moving forward is the validation network for regulatory implementation. And ICCVAM, the committee that I direct, will not only be a key partner, but also all of you are potential key partners in this space as well, through organizations like the OECD, but also through individual companies and regulated industries that are really anticipated to be the first users of NAMs in your R&D pipelines to really help you develop things like better crop protection products. So ICCVAM, I already provided a brief overview of what it is. We have 18 different federal agencies represented in ICCVAM. We keep acquiring agencies, so I feel like that's a good sign. I feel like we're actually doing something right when people want to come and join you. ICCVAM is currently co-chaired by the FDA and the Department of Defense, and then I serve as the executive director and the director of the center that supports it. A couple of key ICCVAM publications over the last couple years. We published a strategic roadmap in 2018. It's still very relevant. We designed it to be an evergreen document. And as a follow-up to that strategic roadmap, we very recently published a new guidance document on validation, qualification, and regulatory acceptance of NAMs. So I won't go into detail on this, but I will say that we have adopted this approach of putting the most important figure on the front cover of the document so that if you don't even open it, you still get basically the take-home message, right? So this figure kind of shows you the key concepts from the perspective of U.S. federal agencies in terms of what's really important to consider when validating and qualifying NAMs for use. And that includes things like the envisioned context of use, the biological and mechanistic relevance, technical aspects, and independent review. Okay, so now pivoting a little bit into some examples of how we have been harnessing AI and machine learning and trying to translate that into application in chemical safety assessment. We have, together with the US EPA, led a number of international collaborative projects over the last several years. Some of you have even participated in these projects, and this is really a way of crowdsourcing machine learning models. And so I have an amazing computational chemistry group in my team, but we're not the only game in town. You know, there's groups all over the world that have their preferred algorithms, their preferred feature sets. And so we've adopted this approach of developing very robust training data that we then share with computational chemistry groups across the world. They apply their preferred method of building models and evaluating them on that training data, and then we give them the identities of test set compounds that we hold back as a validation set. We collect all of these models in-house, we evaluate them both qualitatively and quantitatively, and then we combine the models together using an ensemble approach that really leverages the strengths and compensates for the weaknesses of any individual approach and provides incredibly robust and comprehensive models where you have a minimum of like 5 different models. The last one where we looked at acute toxicity modeling, we had over 35 groups participating, got 120 different models back in. And so for any chemical with a defined structure in the known chemical universe, we have consensus models that provide very reliable predictions. And we've done this for endocrine disruption and for acute systemic toxicity. And these have been part of regulatory guidance documents that have been published by the US EPA and more recently by ECA in terms of reliable lines of evidence to predict things like estrogenic or anti-androgenic pathway activity or acute oral systemic toxicity. And then most recently, we just launched an acute inhalation systemic toxicity modeling project, leveraging these same groups. One really important aspect that I think is often overlooked when validating models, be they computational models or complex in vitro models, is understanding what an appropriate benchmark for performance actually is. So looking, for example, at the acute oral LD50 test, you have a value that is a point estimate for a chemical in terms of the lethal dose, but that value has a confidence interval around it. And that confidence interval is pretty much never reported when you're deriving it from an in vivo regulatory guidelines study. And so when we were curating the training data for the CATMOS QSAR consensus modeling project, we had over 1,000 chemicals that had independently run LD50 tests. And so we were actually able to take a data-driven approach to deriving a confidence interval by bootstrapping through the standard deviations of replicate animal studies. And we found that it's about a quarter log mg per kg per day in either direction. And that is really the appropriate confidence interval to apply, not only when making predictions about the LD50, but also when benchmarking those predictions against reference data. And so when we apply that confidence interval, we see that the QSAR predictions perform just as well as the reproducibility of the in vivo data. We worked very closely with the Humane Society and with the US EPA Environmental Fate and Effects Division to do a retrospective analysis of the applicability of the predicted LD50 value in the context of their risk assessments. So we looked at technical grade active ingredients of pesticide products over the last 40 years and looked at how well the QSAR models would predict the LD50s in comparison to the LD50s that were actually used in risk assessments. And the take home basically was that for non-toxic substances in particular, the in silico predicted LD50 values are extraordinarily reliable. So in fact, if CATMOS predicts an LD50 above 2,000 mg per kg per day, it's 95% certain that the in vivo test would replicate that predicted non-toxic value. We expect this to be the basis of a regulatory guidance policy document that will be forthcoming hopefully in the next couple months. That model and the endocrine disruptor models are part of a suite of QSAR models that can be accessed through the Opera software module. So it's an open source collection of QSAR models that predict not only those toxicity endpoints, but lots of other properties, physicochemical, environmental fate parameters, ADME properties. It's constantly under development and improvement. It's led by Kamel Mansouri, incredibly talented computational chemist on my team. It's available for download for standalone use, like behind a firewall on proprietary data through the NIEHS GitHub. But it's also available through ICE, which is NICEATM's integrated chemical environment. I'll talk to you about that more in a minute. Through the EPA CompTox Chemicals dashboard, through the Precision FDA platform, and most recently through the OECD's QSAR toolbox. So lots of different ways that you can access Opera. Another example of how I think we're really effectively leveraging AI is in really improving best practices around modeling and visualization, and we like to say democratizing access to computational toxicology tools and workflows that were previously the domain of subject matter experts. So we use NIME to build a lot of our pipelines that are available for download for doing modeling and prediction, data mining and curation, analysis and visualization. These NIME workflows are part of a pipeline that we call MOVIS, the Modeling and Visualization Pipeline. And the first example of what we have in MOVIS is a chemical grouping workflow. So this allows you to apply best practices in chemical clustering and classification, both in an unsupervised way and in a supervised way. So instead of doing sort of old school read across where you're like, okay, I've got this, got my Padel descriptors and my Tanimoto score, and those are going to be my structural analogs for my chemicals of choice, no matter what my endpoint is that I'm concerned about, taking a much more informed approach and leveraging both unsupervised clustering and supervised classification and dimensionality reduction techniques to do more intelligent and interpretable chemical grouping for things like selecting test compounds or selecting appropriate analogs for read-across applications. The first example that we did within the Division of Translational Toxicology, we're constantly trying to select compounds for experimental applications. So we want to run a new high throughput screen, or we want to run a new complex in vitro model, and we want to select representative compounds, both that have robust reference data, but also cover structural diversity in across the landscape of chemicals. And so here we can pull and use various unsupervised clustering techniques and various descriptor sets that are driven by users based on their needs and identify clusters of compounds that represent things like food additives or drugs or PFAS, and then use a much more informed approach to select representative compounds for running our experimental studies on. A lot of these concepts are very nicely summarized in a workshop report that was just published a couple months ago in EHP, Unlocking the Potential of Clustering and Classification Approaches, Expert Insights and Applications. So I'd really, really encourage you to download this paper and give it a read. It has a very broad author list and contributor list. It's from a workshop that we did with international experts in this space. Okay, so I promised I would tell you a little bit about the integrated chemical environment. To me, this is really the way that we are trying to deliver our what we call shovel-ready tools that are really accessible and available for prime time application and meet the needs of regulatory decision makers and people in regulated industry that want to integrate NAMS data and also legacy in vivo data that's very high quality, that's very highly curated into their workflows, and also who want to be able to do things like run virtual animal studies or virtual human studies, do in vitro to in vivo extrapolation, but may not themselves be PBPK modelers or fluent in R or Python, and so don't have the tools to access things like the high throughput toxicokinetics R package or various other sort of chemical characterization workflows. So what do you have in ICE in terms of the data? First of all of the data in ICE is highly curated. So we go through a very robust curation pipeline that's both automated and manual. And so you have experimental data for a variety of parameters, a variety of historical regulatory guideline studies, and you have what I think is the highest quality version of the Tox21 and ToxCast high throughput screening data. So in our pipeline, we incorporate the analytical chemistry QC information. So you can see whether a sample was actually in the well and passed QC when it was being tested, or if it failed QC and perhaps you shouldn't trust that data. We also, as part of our curation pipeline, do annotations to mechanistic target groupings, modes of action, things like key characteristics of carcinogens or of cardiovascular toxicants, to provide biological sort of relevance and interpretation ability to the user that may not be as familiar with the actual assay platforms in that high throughput screening data set. A lot of the data that we have put into ICE is historical data that comes from the literature, that comes from regulatory submissions to various agencies around the world. And it takes an incredible amount of resources and time and person hours to curate that data. So wherever we can, we're trying to augment our human intellect by using machine intelligence and machine learning and natural language processing and large language models to make those curation pipelines as rapid while maintaining that robustness and that reliability as possible. And so there's basically sort of three buckets to that. There's first identifying high quality studies in the literature. So studies that adhere to certain minimum criteria from guideline protocols. So, is there a sufficient N to ensure statistical power? Did they use the right animal model, the right dosing route? Are they looking at the right endpoints? So identifying those high quality studies, we've been using machine learning approaches trained on manually curated reference sets to prospectively apply that to the scientific literature. Then the extraction piece. So once you've identified high quality studies, how do you pull out that information in a structured format that's both human readable and computationally analyzable? And then the annotation piece. So then so I like to say that the toxicologist gets a raise every time they figure out a new way to say something. Resorption versus pregnancy loss versus spontaneous abortion. These are all highly related terms that humans understand are basically equivalent, but a machine wouldn't. So automating the application of knowledge organization systems and ontologies to that extracted information is something that we've made a lot of progress on. You can't see it, but there's a citation at the bottom of the screen that's a Foster et al. EHP that describes the annotation piece that we just published earlier this year. We did spend about 5 years working with one of the top natural language processing groups in the world from Oak Ridge National Labs to try and sort of write bespoke code and algorithms to harness NLP to extract information from studies, from PDFs in the literature. And then along came ChatGPT and large language models. And it pretty much rendered the previous 5 years of investment obsolete overnight. But that's okay, because it gave us a really nice reference set and benchmark set to compare the performance of the large language models to. So I have a really, really talented postdoc, Jose Teofilo Morfilo, who is creating extraction workflows that are open source, that are available through NICEATM, that allow you to take zip files with PDFs, and we have a couple of different modes that we're trying here. We're trying a text mode and an image-based mode extraction. We're trying lots of different large language models from Anthropic, from Meta, from OpenAI, and then looking at structured outputs in JSON formats that we can then convert to PDFs or CSV reports. And then we do manual validation to assess the precision of those large language models and extracting that information. And so this just gives you kind of a screenshot of the landing page. So you can upload your zip files, you can decide which extraction mode, which large language model. There's various system prompts. Anybody who works with large language models knows that prompt engineering is one of the absolute fundamentals to achieving success with these models. So this one says, you are a scientific assistant and toxicological expert in reviewing scientific publications, extract and analyze specific relevant information out of PDFs in valid JSON format. Be careful with numbers. And then you have your user prompts. What is the specific instructions that you want the AI to address for each document? What are the variables? So things like daily dosing, animal checks during treatment, body weights, food consumption, et cetera, et cetera, et cetera. And these are obviously customizable, dependent on the study type that you're interested in extracting information from, and allows for consistent extraction and structured data output. So here is sort of the initial, so we started with developmental toxicity studies. Those are some of the most complex study designs. A huge variety of different endpoints that are assessed in prenatal DevTox studies. And first we wanted to assess whether or not those variables were even being considered, and then if so, extract that entity and the source text and then try and convert it to a structured knowledge organization system. We looked at various large language models, and we looked at both text mode and image mode. Consistently across the board, the text mode vastly outperformed the image-based mode. I think that really just represents the training, the effort that's been put into training large language models has been very, very text-centric over the last year or two. And the Claude 3 Opus model from Anthropic was the highest performer, and that's an open source, open access model. And we're achieving, almost 82% precision based on manual review, which I think is really, really impressive. Other things that we have in ICE that are based on both the machine learning models from Opera, but also integrated models such as the estrogen receptor and androgen receptor pathway models. Those are constrained least squares minimization problems that look at a system of in vitro models that are mapped to biological pathways. These were actually formed the training data for the endocrine disruptor QSAR models that I mentioned earlier. Most recently, we also have the EPA's SEAM3. So these are exposure predictions. These are also machine learning models that are trained both on NHANES biomonitoring data, but also on things like material safety data sheets. So looking across, Walmart, one of the largest commercial entities in the world, they have MSDSs on for every single product that they have on their shelves. So you can look and you can see, okay, how are people using various products, and how does that contribute to the likelihood that they're going to be exposed to the chemicals in those products. And so all of that information feeds into the SEAM3 exposure predictions, which are now integrated into ICE. And ICE not only has these databases, but also has these computational tools and workflows that can be accessed via the homepage. And we have lots of user guides and protocols and help videos to help the user navigate through learning how to use these. And this just gives you some screenshots of what you can see in ICE. So as I mentioned, you can explore curated versions of the Tox21 and ToxCast high throughput screening data. You can overlay curves on top of each other for single chemicals, for groups of chemicals. You can filter by mechanistic targets. You can filter by activity concentrations. You can do that in 2D or 3D. You can look at chemical similarity. We're actually about to do a massive revamp of the Chemical Quest tool to incorporate some of those best practices and chemical clustering approaches that I showed you a couple of slides ago in the NIME workflows. We're going to be building that into the next version of ICE. You can run PBPK models to do virtual animal studies, virtual human studies. We have a full instance of the chemicals and products database from the EPA on our backend, which allows you to look at the presence of chemicals in consumer products and then contrast that with their bioactivity profiles across the high throughput screening data. So there's a lot of really cool things that you can do in ICE, and all of these tools talk to each other. So if you run a virtual simulation and you want to send the results of that PBPK modeling output to the chemical characterization tool or to the high throughput screening curve surfer, you can do that. One area where we've really invested a lot of resources is in that PBPK modeling aspect, both from a forward dosimetry but also from a reverse dosimetry perspective. And we've partnered with Jean-Louis Dorn and his team at EFSA to incorporate a lot of the great work that they've done looking at variability in toxicokinetics across a population. So at the moment, the only population variability that's really contained in our PBPK tools are just distributions of parameters. So distributions of body weight, of tissue volume, glomerular filtration rate, et cetera. But actually incorporating things like genetic polymorphisms in metabolic enzymes that are present across the population that really influence internal dosimetry and exposure to, after exposure to compounds, is something that I think is incredibly exciting. So EFSA has done a ton of work on this, and so now we're incorporating the genetic variability and these SNPs that they've observed in enzymes across the population by allowing that to influence the coefficient of variation in the intrinsic clearance parameters in our PBPK modeling workflows. So you can envision that you start with a parent chemical, you use metabolism prediction software to predict both the metabolites of that compound and the enzymes that are responsible for metabolism. You incorporate the variability in that enzyme expression and contribution to the concentrations of the metabolites. So not only do you get the concentration of the parent predicted across various tissues in the body with confidence intervals, you then also get the concentrations, predicted concentrations of the metabolites with confidence intervals that reflect that population variability, that allow you to really, I think, come at more conservative and more protective approaches to understanding chemical risk. And then, of course, you can then apply the OPERA toxicological prediction models, not just to the parent, but also to the predicted concentrations of the metabolites as well. The last thing I just wanted to highlight for you all is a newly published white paper that I was privileged to be involved in from the Reagan-Udall Foundation. This is a nonprofit that supports the US FDA. And this is really making the business case for in silico technologies. So this is actually designed and targeted at lawyers and C-suite executives in companies that might be hesitant to support their scientists' desire to implement in silico and computational models into their R&D pipelines. And so there's a lot of really nice examples, kind of debunking myths. It's a great read, and it kind of makes not only the scientific argument, but the economic argument, which, as we all know, is important in business. Okay, I will stop there. This is the incredible group of people that I am very privileged to lead. And there are several QR codes for accessing ICE, for subscribing to our newsletter. Hopefully many of you are already subscribed. And most recently, we just published in August the ICCVAM Biennial Report, which is an incredible resource. It gives you like a 30,000-foot view paragraph summary of essentially every activity in NAMS across all 18 federal agencies that belong to ICCVAM, as well as the work that NICEATM does in support of ICCVAM. So I'd encourage you to check that out. Thank you so much. Don't know if we have time for questions or not.
Well, actually, we don't, but I think
okay.
we should. We should at least have one question. So no, but it's not your fault. Anybody? Yeah, Ben.
Nicole, thanks very much. Does the database that you use for toxicology only include published data, or also data submitted to, say, US EPA, US FDA, or chemicals?
So it, yes, and. So it includes both, but it has to be declassified before it can be included in the ICE database. So we do source from, scientific publications. We also source from regulatory submissions, but that has to be cleared because ICE is open access, right? We have to make sure that all of the data that's in there is also available, not just through our database interface and our search interface, but also it's all available for download as a flat file. So it becomes public as soon as it's included in ICE. One thing I didn't mention is that we're going to be putting out an RFI, a request for information soon, for nominations of new data sets that would provide significant added value to what's already in ICE. Because we've just been sort of, we've had a backlog and we're kind of working our way through it. And we want to make sure that we're being as comprehensive as possible in meeting the needs of both regulators and regulated industry by what we provide in ICE. So if you have specific data sets that you'd like to see included, please let me know.
Thank you very much. So please give another applause to Nicole.